Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X published on January 8th, 2026, about 3 days ago. It tackles a critical bottleneck in robotics by showing how we can learn world models directly from unlabeled in the wild internet videos, effectively removing the need for expensive action labels. The paper is titled, Learning Latent Action World Models in the Wild, and as we'll see later, the results are really impressive, demonstrating that we can extract usable action plans just by watching diverse video clips. So, Figure 1 illustrates the core motivation by comparing the breadth of actions in different datasets. The green and orange curves show that standard navigation and manipulation data cover only a narrow slice of possible behaviors, effectively limiting models to basic camera or hand movements. In contrast, the blue curve for in the wild videos extends much further to the right. This long tail captures a rich variety of unscripted events, such as new objects entering the scene or people interacting, which are crucial for learning general-purpose world models. Alright, to harness that rich data, Figure 2 outlines the latent action world model architecture. On the left, the diagram shows the training pipeline. Video frames pass through a frozen encoder, f-theta, to produce state representations. Then, an inverse dynamics model, g-phi, compares past and future states to infer a latent action, z. This action feeds into the world model, psi, to predict the next step. Crucially, the right panel illustrates how they prevent the model from cheating by simply copying pixel data. They constrain the latent action using noise, sparsity, or quantization. Well, Figure 3 visualizes exactly how those regularization choices play out in practice. The top row establishes the ground truth, showing a person walking into the frame from the right. In the middle rows, we see that the sparse and noisy continuous models successfully capture this complex entry, rendering a recognizable figure. By contrast, the bottom row reveals that the discrete model struggles significantly, producing only a blurry ghost instead of a clear person, which suggests that quantization limits the model's ability to handle diverse, real-world motion. So, Figure 4 quantifies this gap by plotting the one-step prediction error, where lower values to the left indicate better accuracy. The vertical dashed gray line marks the ideal performance of an unconstrained model, while the red line on the right represents the baseline with no action conditioning. Crucially, the blue and pink bars for sparse and noisy models extend far to the left, effectively matching the ideal. In contrast, the green box for the discrete model stays stuck on the right, barely beating the baseline, which confirms that quantization limits the capacity needed for these complex videos. Alright, Figure 4 showed the model's work, so Figure 5 details how the authors verify they aren't just cheating. Panel A on the left illustrates the scene change test, where they artificially splice two unrelated videos. If the latent variable were simply copying the future frame's pixels, the model would easily predict this sudden jump. However, a real action model fails to explain the sudden cut, which confirms it is learning dynamics. Then, Panel B maps out a cycle consistency check to test transferability. The pipeline extracts an action from video A, applies it to a completely different video B, and then re-extracts it to verify it still works on the original. This ensures the model captures abstract concepts, like walking, that apply across different environments. So, Figure 5 defined the test, and Table 2 reports the actual numbers for action cycle consistency. The columns display error rates for two datasets, kinetics and recon, comparing the original prediction against the error after the full transfer cycle. Looking at the sparse and noisy rows, the transfer values remain impressively low, such as 0.24 for the high-capacity sparse model. Even though there is a slight increase, shown by the multipliers in parentheses like 1.3, this stability confirms that the latent actions capture transferable semantics rather than just memorizing pixels. While the previous results were promising, Table 1 now provides the quantitative proof that the model isn't cheating. It reports the prediction error increase specifically for the scene change test we defined earlier. The critical comparison lies between the without change column, showing baseline performance, and the with change column, where the video cuts abruptly. Notice how the error significantly spikes across all models. For the high-capacity sparse model, it jumps from 0.20 to 0.50. This confirms that the latent actions are learning actual dynamics, which fail during a cut, rather than simply copying the future frame. Wrapping up, the big takeaway is that we can successfully learn world models from messy, unlabeled internet videos by using continuous, regularized latent actions. This approach creates a universal interface that bridges the gap between massive video datasets and real robotic control, effectively bypassing the need for expensive labels. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.